Alright, so we're starting a new chapter, and this chapter is kind of mostly focused on graphing and how calculus can help us graph things. So let's start off with number one here. Find the value of the derivative if it exists at the extremum. Use a calculator to identify the extremum. So let's start with the graph of this, figure that out, and then we'll look at the derivative and see what that tells us. So when we look at this, we should be able to figure out a couple things from the equation. So one of the first things that we notice is that this is odd. Okay, and in fact this one is cubed, but it's S-shaped. Okay, so we know that it's S-shaped, and then the leading coefficient is positive. So it goes up from left to right. So that's important to know because that helps us with what we call hidden behavior. So if we were to graph this on a graphing calculator, so go ahead and type that into your y equals, and when you graph it, it looks like that. Alright, but that looks like a parabola. So that should tell us that there's a problem there. Alright, so the graph kind of looked like this, and then it kind of came back down here like this. So that's what we saw. So that, we should realize, that's not the graph of what we have, because we're supposed to have an S shape, and we're supposed to come up, so this must be coming back up over here. So there's a couple ways that you can handle that. You can go to zoom, hit F2, and there's some different choices. There's zoom out, so you can try zoom out, see what that does. It says where do you want your center to be, just keep it at the origin. So it's telling us it's busy as it graphs this. So now it's come back up over here, but I still can't see the minimum and maximum. So I don't like this over here, I don't need this over here, so I'm going to cut these down and I'm going to stretch it out that way. So I'm going to go up to the window, and I don't need to go that far, so I'm going to go -20 and +20. But the y, I need to go up and down a lot farther, so I'm going to try -400 and +400. And I'm going to see what that does. So that's good, and so I almost got it down here. So I don't need to go that far up there, maybe 100 instead, and a little bit farther down here. So I'm going to go back to the window, and what did I say, maybe -500, and I only needed to go 100 here, and maybe I'll go by 50s. Okay, so that's a little awkward, but alright, so now we have a nice view of that. So it's kind of going like this, and like this, and like that. Okay, so we fought through that hidden behavior to get a better picture of what it looks like. Now we want to know the extrema, the minimums and maximums. So we're going to actually hit F5, and it says maximum. So I want to calculate the maximum. So it asks for the lower bound, so I want to go on the left side of that and hit enter. And then I want to go on the right side of that and hit enter. And it's going to give me the value. So the maximum is -2 and 61. Now you can see that this goes up forever. So this is a relative maximum. So we have a relative max, and this is a concept you should have talked about at least last year, maybe the last 2 years. So this is at -2 and 61. That's a relative maximum. Now I'm going to come over here, and because this goes down forever here, this is going to be a relative minimum. Now, another way they talk about it is local. So there's local, some people call that a local maximum and a local minimum. Now, if this was a parabola can have an absolute minimum or maximum. Okay, so absolute or global. Global would be like the whole world, the maximum of the whole world, the minimum of the whole world, the whole thing. Local means relative in a certain area. So if we go back to the calculator, and now we can go F5, and there's a minimum. So now lower bound, left, hit enter. Now you can arrow over here to the right, but you can also type in a number. So I could have typed in 12 and it just would have put it over here. But now I'm on the right side of that. I'm going to hit enter. So I have a relative minimum at 8 and -439. Okay, so the question was, find the value of the derivative at the extremum. So let's take the derivative of this. So the derivative of this is going to be 3x squared. And you know how to take the derivative of this, so this would be a good place to pause and make sure that you're getting some practice, that it matches up. Okay, so we have that. So if we factor out a 3, we would have this. 3 goes into there 1 6 times. So that's, let's see what happens here. So 2 and 8, -8 plus 2, so +2, -8. So if we look at that, we get x equals -2 and x equals 8. And if we look, what were those when we set the derivative equal to 0? If we set the derivative equal to 0, then x equals -2 and 8. So when our derivative equals 0, we know that we have either a minimum or a maximum. Okay? So if it says where is, for example, where is a relative maximum? That would be -2. That's the x coordinate. And what is the maximum, relative maximum? That would be 61. Where? What? Where does it occur? -2. What is the relative maximum? 61. Okay, critical number, critical point. A critical point is a point in the interior of the domain of a function f at which the derivative equals 0 or the function is not differentiable. Okay? But it has to be defined. So that's important. That's the definition of a critical point. Extreme values only occur at critical points and endpoints. So a minimum or maximum could occur at an endpoint. A critical point is not necessarily an extreme value. For example, y equals x cubed has a critical point at 0, 0 because f prime of 0 equals 0. The derivative of that's 3x squared. And at 0, that equals 0. However, 0 is not an extreme value. So it's not a biconditional statement. It doesn't work either way. Okay. The extreme value theorem is on page 60. It says if f is continuous, and so that's something that's important on the AP exam, to state that stuff is continuous, then f has a minimum and a maximum on the interval, on the closed interval. So if something's continuous between here and here, there has to be a minimum and there has to be a maximum. And it could be the endpoint, but it could go way above, way below, whatever. But you have to have a minimum and a maximum. You have to have an extreme value. Okay. Make sure, I should have moved that up. There's the extreme value theorem that I was just talking about. Okay. Make sure that you get in the habit of putting f prime of x equals 0, because sometimes they give a point on the AP test for having that in your work. because it shows that, well, it shows that you memorized that your teacher told you to put f prime of x equals 0. But we use that for a few different things, like we just did up there to find minimums and maximums. So we want to keep that in mind. All right. So if we want to find the critical numbers, we need to take the derivative, and we need to see where does the derivative equal 0, and where is it not differentiable. So this is a quotient rule. This is good practice. You guys should pause and practice the quotient rule. So remember, the quotient rule starts with low and ends with low. So low d high minus high d low over low squared. All right. So how much of this can we do in our heads? So that's going to be 4x squared minus 2x squared. That's going to be 2x squared. And that's going to be plus 8x. And that's going to be it for that. And then this is, all right. So I just said f prime of x equals 0. That's what we're looking at. So if we set that equal to 0. So first of all, for a rational expression to be equal to 0, the numerator has to be 0. The only way to get a fraction to be 0 is for the numerator to be 0. Okay? So if we factor that out, that's going to be, factors out of there 2x. And that leaves us with x plus 4. So if we set that equal to 0, we're going to get 0 and negative 4. Okay? Now, where is it not differentiable? So it's not differentiable at x equals negative 2 because that would be dividing by 0. But that's not a critical number because f of negative 2, let's put it this way, it's getting messier and messier, because f of negative 2 does not exist. If you go back up here, f of negative 2 is not defined. We can't plug negative 2 in there, we'd be dividing by 0. So that's not a critical number. Not differentiable is where the where the denominator equals 0. So not differentiable is where the denominator equals 0. And where a rational expression equals 0 is where the numerator equals 0. Okay, so our answers came out here. Now, on a Chapter 3 test that I normally give, I don't know if I'll be putting that version online, but this would be a multiple choice question. It would have all of these choices, and some people would select A because of this. But that's not, by definition, a critical number. Now, the thing about this is we're actually going to use this number to do other things. So don't let that throw you off. So the answer we want here is B. It's 0 and negative 4. Those are the critical numbers. All right, so let's do this again. So we want to know where f prime of x equals 0. So we're going to take the derivative here. F prime of x, that's going to be 2/3 times 3x plus 1. Subtract 1 from that, plus from now on you always want to ask yourself, do I have to use the chain rule? So the derivative of the inside is 3. Alright, so that's going to cancel, and we're going to set this equal to 0, and that's going to be 2 over the cube root of 3x plus 1. Alright? Now, the numerator here does not equal 0. So the derivative is not equal to 0 anywhere. Now, the denominator, where is this not differentiable? The denominator, if we set that equal to 0, and we cube both sides, we would get 0 equals 3x plus 1. So that's going to be x equals negative 1/3. Now, that is defined. F of negative 1/3 is fine, just 0. So, just said that f of negative 1/3 is defined. It equals 0 if we plug it in up there. Not sure how much of that you need to see. 3 times negative 1/3 plus 1 to the 2/3. That's going to be negative 1 plus 1. That's going to be 0 to the 2/3, which is 0. Okay, so our critical number is negative 1/3. So it's not just because we're dividing by 0 that we throw that answer out right here. The reason we threw this answer out was because it didn't work back in the original function. And the reason that we're okay with this one is because it does work in the original function. All right? Now, the key to this is when you are asked to find an absolute minimum or maximum, you have to check the endpoints. Don't forget to check the endpoints. Another clue is that they have brackets. So all of these things are clues that you're finding an absolute extrema. Brackets, the word absolute, if you have a graph that closed endpoints. So, when you see the word absolute, you want to make sure that you make a candidate table. So a candidate table is going to include the exponents. So that means we have f of negative 2, and we're going to have f of 4. Both of those. Alright? So, if we plug negative 2 in here, now the candidate table we're plugging into the original function, and we're just testing to see, like, what are those values. So, negative 2 cubed is negative 8. So that's going to be negative 16. Negative 2 squared is 4. That's going to be negative 12. Negative 2 in here, that's going to be plus 24 and plus 5. So that's negative 28. That's negative 4. That's 1. Okay, so in this case, we're just looking at what are the actual values. What's the biggest one and what's the smallest one? So now we're going to plug in 4. So 4 cubed is 64 times 2 is 128. 4 squared is 16 times negative 3 is negative 48. 4 times, that's negative 48 and plus 5. So that is 80, 96. So 96, 4, 32. 32 and 5 is 37. So far, that's the biggest number and that's the smallest number. Now, to find any numbers in between here, now we're going to take the derivative and set that equal to 0. So f prime of x equals, and again, pause. You know how to take this derivative, or just do it real fast. Do it faster than me. Okay, so if we set that equal to 0 and factor out a 6, so that's going to be x minus 2 and x plus 1. Okay, so we have critical numbers when x equals negative 1 and 2. Alright, so the first thing you do is, do these lie in that interval? if any of these numbers lie outside of that interval, we don't have to check them. But both of them lie inside here. So we need to check -1 and 2. Okay, so -1. Now, these numbers get plugged back into the original function to test them. We're trying to find out the biggest and smallest numbers in f. So -1, it's going to be -2, and plus -12 times -1 is +12, plus 5. That's negative, that cancels out, so that's 12. Okay, here 2 cubed is 8, times 2 is 16. 2 squared is 4, that's -12. That's -24 plus. So that's -36. That's -20 plus 5 is -15. Okay, so literally all we're going to do is look at those numbers and identify the smallest and the largest. So this is the smallest number, so that's the absolute minimum. The absolute minimum is right there. And this is the biggest number, so that's the absolute maximum. All right? I don't know, that messes some students up. But on the AP test, they're looking for a candidate table if they ask for the absolute minimum or maximum. The extreme values, Extrema. I don't have this stuff highlighted because it's all testable. So if you want to highlight all 6 examples, go ahead and do that. All right, so let's try that again. So we need a candidate table. So the first thing is going to be f of 0. So if you plug a 0 in there, you get 0. And we're going to need f of 4. And I'll just tell you, this is one I prepared earlier. Just trying to be funny, like on a cooking show, you know, and they already have one cooked in there. Anyway, it's 11.314 if you plug in 4 into that on the calculator. Okay, so now we want to test a relative extrema in between there. So we're going to take the derivative of this. So that's going to be 5/4. The 4's cancel out, so that's going to be 5x to the 1/4. And then bring that down, it's going to be -2. It's going to be x to the -3/4. So this is one of those things that I've tried to show you a couple times. That fraction, that negative fractional exponent. So that brings us to this situation. So now we're going to get a common denominator here as we set that equal to 0. And so we're going to multiply this by x to the 3/4 over x to the 3/4. And this always simplifies nicely, the numerator. So that's going to be, add the exponents together, that's x to the 1st. So that's just 5x minus 2. And the denominator is x to the 3/4. So if we set that equal to 0. So now if we go back, the numerator is 0 at 2/5. And the denominator is going to be 0 at 0. Okay, well we already have 0, so that's fine. So we need to test 2/5. So if we plug in 2/5, I also did that earlier, so that's -5.090. And you do need to have that last 0 on there because it needs to be to the thousandths place. So now looking at those 3 numbers, this is the absolute minimum, and this is the absolute maximum. All right? Okay, so candidate table again, because it's an absolute. There's the directions for all these. So we've got f of 0, and we have f of 2 pi. So the sine of 0 is 0, cosine of 0 is 1, 0 times 1 is 0. Okay? And 2 pi, sine of 2 pi is 0, and 1. 0 times 1 is 0. Okay. Memorize the routine. It's not that hard. Same thing over and over again. It's 3 times in a row. Plug in the endpoints. Plug in the endpoints to the original function in a candidate table. Then take the derivative. Now, this is a product rule. So the derivative of the first thing, derivative of sine is cosine. So I'm going to have cosine times cosine. So I'm going to put cosine. Better not. All right, cosine, derivative of the first thing times the second thing, plus the first thing times the derivative of the second thing. That's good practice on your trig derivatives. Hopefully you know those. Negative sine. So that's going to be cosine squared minus sine squared. Now, we don't want, we're trying to solve this, trying to set this equal to 0. One of the things we want is we want stuff multiplied together, or we want all one, I forgot the x there. Don't forget those x's, those angles, thetas, whatever. I would like to get this down to one function. Well, if you think about it for a second, there's the Pythagorean identity. Sine squared plus cosine squared equals 1. So if we substituted, sine's going to be 1 minus cosine squared. So we can replace that with 1 minus cosine squared. So that is going to be, that's going to be minus, that's going to be plus. So I'm going to have 2 cosine squared x minus 1. So if I add 1 and divide by 2, and take the square root of that, so we're going to have cosine x equals, we'd have the absolute value, so it's going to be plus or minus, and if we rationalize that, that's root 2 over 2. Now, maybe somebody is watching this and they say, you said we don't have to rationalize denominators anymore. We don't. But since most of us have it memorized as root 2 over 2, that's probably going to work out better for us. If you know that that's pi over 4, then that's fine. But I switched it because most of us probably don't. So when does the cosine equal plus and minus root 2 over 2? At pi over 4, at 3 pi over 4, at 5 pi over 4, and at 7 pi over 4. Now, hopefully we all realize that pi over 4 and 3 pi over 4. Now, when we go back around to 5 pi over 4, they're both negative, so that will be the same as pi over 4. And here, one's negative and one's positive, the same as here. So I'm going to get the same answers for these two as I get for these two. So I don't really need to check all 4. I can just check 2. So if we plug in pi over 4 to the original function, the sine of pi over 4 is root 2 over 2. And the cosine of pi over 4 is also root 2 over 2. So if we multiply those, that's 2 over 4, which is 1/2. Okay? Now, if we plug in 3 pi over 4, the sine of 3 pi over 4, that's a positive y value. So sine, that's going to be positive root 2 over 2. Now, the cosine of 3 pi over 4, that's over in the second quadrant, and that x value is negative. So that's going to be negative root 2 over 2. So that's going to be negative 1/2. All right? So, and again, I said these two values would repeat. This would give us positive 1/2, and this would give us negative 1/2. So the question said, find the extrema. So these are the extrema. So this is the absolute max, and this is the absolute min. Okay? Now, if it said where does the absolute maximum occur, I'd have to say pi over 4 and 5 pi over 4. Where does the absolute minimum occur? At 3 pi over 4 and 7 pi over 4. All right, last one. Okay. So again, candidate table. Very repetitive, same thing over and over again. So f of negative 1 and f of 3. Okay? So if we plug negative 1 in here, negative 1 is less than this. Negative 1 squared is positive 1. 3. 3 is greater than 1. If we plug 3 in here, 3 times 3 is 9, minus 2 is 7. Okay. Now, take the derivative of that, f prime of x, that's going to be 2x for x is less than 1, and it's going to be 3 for x is greater than 1. Okay, so we want to know, when does f prime of x equal 0? Well, 2x equals 0, divide by 2. That happens when x equals 0. So we can do that, f of 0. Now, when is it not differentiable? Well, if you look at these two things, at the boundary point, f prime of 1 from the left is 2, and f prime from the right of 1 is 3. And so those do not equal. That means that at 1, at the boundary point, the derivative does not exist. So I have to test that value as well, and I think that's behind. Okay. So if we plug in 0, 0 is here, so that's 0. And if we plug in 1, when it's equal to 1, it goes in here, so that's 1, so that's 1. So this is our absolute max, and this is our absolute min. All right, and I'm a little worried because they haven't made the announcement yet, so I'm wondering if I'm going to get setting the alarm off. Have a good day. See you later.